So using this formula for the unit tangent vector, let's try to apply that to the first example here. So find the unit tangent vector for each of the vector value functions, even though we just have one here for the example. And we're going to revisit this example again at the end of this lecture when we cover the normal and binomial vectors. But for now, given this vector value function, so this is basically the circular helix. Given that the first component is cosine of t, the second component is sine of t, and the last component is t. And okay, so to find the unit tangent vector, again, you need to find the tangent vector first. So you take the derivative of a vector value function. So given r of t, we have of cosine of t, sine of t, comma t. You have the tangent vector to be negative sine of t, cosine of t, comma 1. So again, this is the tangent vector. So next, you need to find the magnitude of the tangent vector. That is, so this is equal to the square root of negative sine of t square plus cosine of t square plus 1 square. Right, so you have under the square root is sine of t plus cosine of t. Sorry, sine square of t plus cosine square of t plus 1. Right. But sine squared of t plus cosine square of t is equal to 1. So you get the magnitude of the tangent vector to be root 2. Any questions on this calculation? All right, so now we have enough information. I'm going to calculate the unit tangent vector. So the unit tangent vector is capital T of t equal to r prime of t divided by the magnitude of r prime of t. Get negative sine of t, comma cosine of t, comma 1 altogether divided by square root of 2. You can leave it like this, or if you want, you can actually rewrite this a little bit to show the scale of tangent vector. That is 1 times square root of 2. Sorry, 1 over square root of 2 times the magnitude and the tangent vector, negative sine of t, cosine of t, comma 1. So this say that you have the tangent vector and it's scaled by 1 over square root of 2. Therefore, you're going to obtain the unit tangent vector. Oh, any questions on this calculation? We good? Right, straightforward calculation, I hope. Now let me move on to the two vectors, that is the unit normal vector and binomial vectors. Okay, so when I say binomial vector, it is assumed to be a unit vector as well. Okay, later on I will drop the unit word and just say normal vector and binomial vector, but it's always going to be assumed that they are unit vectors, and you will see why they are unit vectors. All right, so first the unit normal vectors, and it's going to be the inward vector. You have outward unit outward normal vector, unit normal, and inward normal vector. So outward normal vector, usually you see that in creating a plane in multivariable calculus. when you have a vector on the plane and the outward normal vector. Right? So, but in this case, you have a unit normal vector. This case called the inward normal vector. So definition for unit normal vector, let capital C or fancy C be a smooth curve represented by part of T open and over an open interval. Now, if capital T prime of T is different from 0, then the unit normal vector is defined as, you have capital N of T to indicate that this is the unit normal vector. A unit normal vector is equal to T prime of T divided by the magnitude of T prime of T. All right, so let me derive this formula right here to show you that why the unit normal vector is equal to this fraction. Okay. So let me start with the fact that the unit tangent vector is a unit vector. Okay. Since capital T of T is a unit vector, we have that the magnitude of a unit vector is of course equal to 1. Or the magnitude square, it is equal to 1, right? You just take a square on both sides of the equations. But now in terms of the dot product, there's the property that we cover when we talk about the dot product, that the magnitude square is equal to the dot product of the vector itself, right? So T dot with itself is equal to 1, or so nothing fancy there, right? We just basically show that the unit tangent vector is a unit vector. That's it. Right? Now, what the next step is to differentiate both sides of these equations, right? And when you differentiate this left-hand side, the left-hand side, you use product rule, right? So differentiate both sides of the equations. We obtain that T prime dot with T plus T dot with T prime is equal to 0. So you have 2 of this, right? You divide both sides by 2, so 1 of this is equal to 2. So you get that the unit tangent vector dot with T prime is equal to 0. Okay, So for the properties of the dot product, right? When two vectors dotted together and equal to 0, that means the two vectors are orthogonal or perpendicular to one another. You're with me on that? Okay, so this particular equation implies that t and t prime are perpendicular or orthogonal to one another. So this implies that t and t prime are orthogonal. Then we define that vector t prime to be a normal vector. Not the unit normal vector, just the normal vector. Of the vector value functions. And thus, the unit normal vector is defined to be capital N of t, right? Because t prime is the normal vector, so to normalize that or to find the unit normal vector, what you do is you use t prime, then divide it by the magnitude of t prime. Okay, so that's how you derive the unit normal vector. Okay. It's coming from the idea of the unit tangent vector, and this unit normal vector is orthogonal to the unit tangent vector. You okay with that? Okay. All right, so you can apply this into both the spay curve or the plane curve, right? No matter what you want, it's still there, because these are just the vectors. Okay, so as for example, if you have a circle, right, on a plane curve like this, and at every point you can track the movement of the particle at every point along the circle, right? So at every point you can track the tangent vector. Okay. Or in this case, of course, the unit tangent vector. And remember, at every point here, you have a tangent vector. And by our derivations, you have the unit normal vector is going to be orthogonal to the unit tangent vector. Okay. So therefore, have this. Good. And again, at every point, you have one tangent vector, unit tangent vector, and one normal vector. Okay. You okay with that? And it just go moving along the circle with both tangent vector and normal vector. Okay. You okay? You good? Any questions on this? Okay. Inward normal vector, because we define it that way, and it will help us to see more clearly why is the inward normal vector through this relationship of the TDS equal to kappa times the unit normal vector. All right, so we're going to, by showing this, we can show the relationship between the unit tangent vector and the normal vector through the curvature, and therefore track the movement of the particle along the spay curve or the plane curve. Okay. We have this, to show this, we applied technical chain rule, and we see these derivations the last time in lecture 6 already. So apply a chain rule on the vector dt dt. We have that dt dt equal to dt ds times ds dt. So this is just the regular multiplications. Now I'm rearrange these equations to solve for dt ds. So dt ds is equal to dt dt divided by ds dt. Now what do we got? So for ds dt, anyone remember what ds dt means? In the last lecture, lecture 6. All right, so let me go back to lecture 6. Right, so S is the notation that we use for arc length. Okay, and over here, okay, so ds dt means the speed of the particle at a given time t, right, along the curve. So ds dt is equal to the magnitude of the tangent vector. You okay with that? All right. So we're going to use this formula for our derivations. But we have that ds dt equal to the magnitude of r prime of t. And we let t prime of t equal to capital dt dt. Then we have that dt ds equal to t prime of t divided by the magnitude of r prime of t. Now, what are we working on? We want to show that dTds equal to kappa times the unit normal vector. Okay. So on the left-hand side, you get dTds. We are good with that. All right. But on the right-hand side, somehow you have to make the curvature appear and you have to make the unit normal vector appear in the equations. Okay. So let's make the curvature appear in the equations. So what is the formula for the curvature? Right. So kappa is the curvature. We have two formula for the curvature. Right. So we have one that is the magnitude of dTds. Right. So how fast you want to see the unit tangent vector change, right, with respect to the arc length. Okay, so that's the definitions. Now you need to use the alternative formula, right? So the curvature is equal to what? The magnitude of, yes, yes. So that is what you get, right, for the alternative formula. Okay. Now, what do you see in the formula? In our derivations right here. So in our derivation in the denominator, you have the magnitude of tangent vector, magnitude of r prime. So r prime Magnitude of r prime is equal to what? The magnitude of t prime of t divided by kappa. You okay with this? Just switch place. Okay. So in addition, you see that the magnitude of r prime of t is equal to the magnitude of t prime of t divided by kappa, where kappa is the curvature. Then you have that dt ds equal to t prime of t divided by the magnitude of t prime of t over kappa. Now, when you divide fractions, you can multiply by the reciprocal. Right. Well, this is equal to kappa times t prime of t over the magnitude of t prime of t. Now for this fractions right here, t prime of t over the magnitude of t prime of t, what is that equal to? There you go, the unit normal vector. So therefore you have kappa times unit normal vector. So that is the derivation. Yes. One more time. Yes, 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 yes. Any any other question? Okay. So that is again the relationship between the unit tangent vector and the unit normal vector. Now let's move on to another vector. It's called the unit binomial vector, but most of the time we just say binomial vector. Okay. So the unit binomial vector is very straightforward. It's just the cross product between the tangent vector and the normal vector. Okay. So the unit binomial vector denoted as capital B is defined to be, so capital B equal to T cross with N. Right, so since T is a unit vector, N is a unit vector, therefore B is also a unit vector. All right, because of this relationship, we have a few notes here. So B depends on the cross product between T and N. So B is going to be orthogonal to both T and N. So since T and N are a unit vector, B is also a unit vector. So in two-dimensional case or in plane curves, so in R2, B is either pointing upward or downward. That is T and N create a plane, and B is normal to that plane. Yes, in R2. Okay, so let's say you have this plane right here. Plane, right? There's a circle. You track the movement of the particle, right? You know that there's a, I need more pens. I don't have more. You look at this. All right, so as everyone can see up here on my plane. Okay, so imagine there's a circle right here moving along, right? If I track a movement of the particle, right, along this circle, I can track a tangent vector at every point. And with respect to that point, with respect to that tangent vector, there's the normal vector pointing inward. Okay, and I have a binormal vector right here. So I have a three vectors moving, right? So is moving. Now I just going to focus on this binormal vector. Okay, so the curve move, the particle move along the curve. As you can see, the binormal vector just pointing upward. Or it depends on the movement. So this is my directions. My point of view, this is counterclockwise. If it's moved in clockwise directions, the binormal vector is going to point down. Okay, so to illustrate this bullet point that the binomial vector in plane curve is just pointing upward or downward. But in terms of space curve, so in three-dimensional case, in R3, B is changing as we move along the curve. Thus, B changes with respect to the arc length of the curve. When you're done with the writing, I want to show you a simulations on the movement of a space curve and plane curves. Huh? Plane curve. Or planet Earth. You done with writing? Emil? Write faster. Pushing. Done? Good? All right. All right, so let me show us simulations here, okay? So as you can see here on the simulations, on the illustrations, a helix, right? But let me show you a circle first, and then I go back to the helix in a minute. So let me go and change. All right, so the setup here is that you need the first component, the second component, the third component. In this case, the third component is going to be equal to 0, okay? And you just need the first and the second component, and the first component is cosine of t, the second component is sine of t, so therefore is the vector value function or the parametric form of the circle. So let me change this to 0. Where is it? Okay, so you have a circle right here. All right, so you have the blue vector is the normal vector, the yellow vector is the tangent vector, and the purple vector is the binomial vector. Okay, now let's stop there. If you follow this point of view, fine, and let's change the parameter here, parameter t. So t is between -2 pi, -10 and 2 pi for some reason. All right, but you know what I mean, okay? So let's track it so it can move in one certain direction to see that the binomial vector is just pointing upward. You okay with that? Okay. So now let me go to the helix case. Let me change this to, why just popping up? Okay, now I have the helix, okay? And you can see that, let's take a look at the particle right here and tracking the 3 vectors, the tangent vector, normal vector, and binomial vector. And you can see the normal vector is always pointing inward, right? To kind of like toward the center of the helix. The tangent vector is easy to see. You just basically look at the tangent line along every point along the curve. The binomial vector, I will talk a little bit about that later, but will change depend on the positions of the particle. All right, so let's run the simulations now. All right, so the normal vector is just kind of pointing inward toward the center of the helix. Tangent vector is fine. The binomial vector will change. The parabola vector will change, depends on the locations of the particle. So remember the last bullet, so that's the simulations. Took me a while. All right, so let me go back to the last bullet here. So B changes as we move along the curve, right? Or in other words, B changes with respect to the arc length of the curve. So in this way, how could you track the change of the binomial vector? Again, you go back to the definitions of the binomial vector. That is the cross product between the tangent vector and the normal vector. Okay. And also, B is orthogonal on both T and N. And then again, when T and N, they orthogonal to one another, they create a plane. You with me on that? And the binomial vector is normal to that plane. Okay. So as you track the points along the curve. Okay, T and N create a plane. You with me? In space, a plane in space, and the binomial vector will be normal to this plane. Okay, and as the particle move, this plane going to turn around like this, moving back and forth, depends on the locations. It's no longer fixate on certain area. Like, so this plane is fixed no matter how you move it, right? No matter how the tangent or the normal vector move it. But in space, this plane going to just twisting around. You with me on that? Okay. Or turning around. Okay. And we can track all of this movement through these formulations. This is called the Frenet-Serret formulas. Okay. This is kind of the fundamental importance of a branch in mathematics called differential geometry. All right. So if you bring this formula to talk with Dr. Usa, he's going to love it. Right? He's a big fan of differential geometry. And this is kind of like the very basic information about differential geometry, that you can track the motions of certain particle along the curve using the unit tangent vector, unit normal vector, and unit binomial vector through these three equations. All right, so the first equation, you already see that earlier. That's tell you the relationship between the unit tangent vector and the unit normal vector through the curvature. And the last two is a little bit vague, and at this point, you don't know what that is. But through certain example that we're going to cover, example 3 and example 4, it will tell you the relationship between the binomial vector and the normal vector, right? Through through a constant called torsions. Torsion means how much you twist the plane. You have this plane, how much it's going to get twisted. And okay, so equation 3 tell you the relationship between binomial vector and normal vector. And the second equations tell you the relationship between all three equations, all three vectors, sorry. Okay, and for the second equation, that's going to be one of the questions in the written homework I'm going to give you. All right, but we're going to use the information. I will tell you how to do it. So it's just going to you will not go in there blindly and do the problem. It's difficult to do so. It's a little bit different. So you apply a torque in one direction. How would you make the twist? You apply the torsion in the opposite directions. Okay, but in the next two examples, we will help us to derive the equation 3. Equation 2 is for homework, because it's a little bit harder, of course. I'm gonna give you as the homework. Awful, yes. Okay. Not yet. It's not going to be on webwork. It's the written homework, not online homework. Okay. So most of the time when I give a problem in the written homework, I give this formula too, and it's most of you can do it. If not, come to talk my office. It should be fine. Okay. I guarantee. I promise. Sure. Okay. So to derive the third formula, we need two examples. So the first one, that we need to show that the BDS is perpendicular to B by using the fact that B is the unit vector. So we're going to follow very similar procedure as we see in these derivations right here. Okay. So in these derivations, we show the relationship, or we show the formula of the unit normal vector. And this unit normal vector can be derived from the fact that the unit tangent vector is a unit vector. So we're going down here, we're going to use the same idea that Given B is the unit vector, can you show that dBds is perpendicular or orthogonal to the binomial vector? All right, so since B is a unit vector, the magnitude of B is equal to 1, or B squared, the magnitude of B squared is equal to 1. Instead of writing like that, you use the fact that B dotted with B is equal to magnitude of B squared. That it's dot product. Now, the next step is to differentiate both sides of the last equations. We got that B prime dot with B plus B dot with B prime equal to 0. All right. So when you use the dot product here, there's no specific information about the independent variable. Okay? This is true for any independent variable when you differentiate both sides of the equations. All right, so earlier in the example, we use dt, d capital T, d little t. In this case, we want to show dBds, so the derivative in this case is with respect to the arc length. Okay, so B prime in this case is going to be dBds. So you have dBds dot with B plus B dot with dBds equal to 0. All right. So these two terms are the same. So therefore, you have that B dot with dBds equal to 0. So this shows that the binomial vector and dBds are orthogonal to one another. Okay, so that example 3, we just show that B and dBds are orthogonal or perpendicular to one another. Now let's move on to the next example. What we want to do in this example is that we first want to show that dBds is perpendicular to the unit tangent vector using the fact that B is equal to T crosses with N, right? Then we're going to deduce that dBds is parallel to N.